see if we get Mike Johnson on screen. Yes, definitely. We've got you here. Can you help me and try to do your presentation, share your presentation with us? Because we'll be getting ready to go in a little bit. So if you go to present down below, and then it goes straight to your screen. Because we had a really good session just now with Andrea and Hassan, of course, because they gave a lot of data. You know, my feelings on the PF curve are always very mixed. You know, I love it, but you know, it's that Christmas tree at the end and trying to figure out the right points. So I love that they gave so much information on being able to get that PF curve sorted and how they can do that. Because a lot of times that's one of the areas that a lot of reliability engineers have trouble with. So I'm glad they cleared up a lot of that information. And I definitely, I have a preference for the lubrication side of things. So, when they ask the question about vibration versus lubrication, you know, I have a little bit of preference, but that's just me personally. We can do both. When you do both, it definitely helps. So I think if we get down to the bottom of the screen, there's a present button straight down to the bottom of the screen. And when you click present, it should help you to share your screen, if that helps at all.
Okay.
Yeah, we will try that.
Screen,
Yeah.
entire screen. Here we go.
Yes. Let me see. I'll
All
see if
right.
it comes up.
The share screen is still grayed out, or the share button is grayed out.
Ah.
Entire screen. Okay.
Mm-hmm.
And now I can see that. There we go. Here we go. Right. What do you know? Magic.
You got it. And let's go to your presentation.
Okay.
So I'm gonna add this to the stage, and we will be getting ready to go. Because I know everybody's excited to have you here, Mike. Everybody wants to hear about this cost center, moving from a cost center to a competitive advantage. Because I think that's one of the things that we always hear about within this sector. They think that everything is a cost center, everything is a lot of they have to prove this to the budgets, they have to prove this to finance. So I'm gonna give it over to you because you are the expert here,
Thank
and
you.
you will be helping us to find out on how to move it from a cost center to a competitive advantage.
Can you
So
hear me all right?
yeah,
Very good.
you're all good to go, Mike.
All right. Thank you for the opportunity to visit. And I'm trying to page forward on my, here we go.
Yes.
A little bit of information about me. This can be provided to you after the fact if you like. A little bit of information about the various things we do here. We focus on mechanical reliability improvement through everything related to machine lubrication, except selling lubricants. We don't do that. Why is machine lubrication considered a pathway to improve financial stability? We've been told by the people that study our bearings in the dynamic film that supports the bearings, that floats the elements in the races, that our industrial world floats on a 10 micron film of oil. The better our research gets, the more we see that we're not quite so lucky. The reality is we're floating our element bearings on a 1 micron, well, 0.5 to 1.5 micron, and our journal bearings on a 3 to 10 micron thick oil film. Now, on the one hand, that's extraordinary that works, and it does work. On the other hand, realize that we're trying to live our industrial livelihood on an oil film the thickness of a red blood cell. It's a precariously thin layer of protection. We recognize with our day in, day out activities that we have to do whatever's necessary to sustain that red blood cell thick layer of protection in order to protect productive capacity. If we lose our oil film, all of the effort we put into installation, alignment, and balance is lost. It's gone. So our day in, day out activities should be focused on doing whatever's necessary to preserve that precious oil film. When we lose that film, we suffer wear from surfaces rubbing, wear from contamination, wear debris and atmospheric contamination. Contamination leads to fatigue, suffer wear from corrosion, and all of those things generate lost productive time. And it doesn't really matter whether our repair activities are scheduled or unscheduled. Once time is gone, it's gone. We lose machine repeatability, which impacts product quality. We have increased risk of injury. We have a higher cost of production per unit, whatever it might be, all of which contributes to lost competitive position for our company, for our enterprise. The people that supply our machine parts recognize and actually support doing things that are above and beyond the perceived call of duty to protect our bearings and our other lubricated machine parts. Here's a slide from SKF data showing the proportion of lubrication-related factors leading to premature bearing failure. Schaeffler FAG bearing says, yeah, that's close, but actually it's not 57%, it's 80% of contribution premature failures comes from defects with our lubrication plan. These defects are all measurable, predictable, and avoidable. So what? With all the things that you have to do, why would you bother investing more effort, more money, more time into trying to address something you're already doing, but address it more effectively? Well, time is money. You all have all heard that, I'm sure. What can you expect from deploying a more precise lubrication work plan, precise product selection, precise quantity, precise volume, precise contamination control, precise location? What we would expect to occur would be reduction in replacement of lubricated machine parts. A reasonable target is 25% reduction. An ambitious target would be 50% in the frequency of repairs over a 3-year period. Elimination of labor associated with those repairs, any contract labor associated with those repairs, and far and away, more importantly, increased net production output. Regardless of the cost it is incurred to replace machine parts, that dollar value pales in comparison to the potential of increasing production output without adding new production machinery. There's various different ways companies go to about measuring success when making improvements. Here's a kind of complex chart, but it shows the deployment of a contamination control, a key element of machine lubrication, over a multi-year period that concurrent with increased fluid cleanliness, obviously, that's expected, but also increased output liters per second, part of a design plan. Here's a similar chart showing an 8-year progression in pump replacement decline following implementation of contamination control. Another steel mill in Japan showing very similar results over a 5-year period. A major paper mill where they actually got into the hard cold numbers showing that the deployment of precision lubrication program, storage and handling improvements, training, contamination control, and the implementation of the program itself over a 5-year period, with 2015 being year 1. And regardless of what this very large mill spent, the key point is here, the estimated return on investment from their metrics, from their operation, $500,000 spend and $8 million savings, a 1,553% return on investment. I've done multiple cost analyses during benchmarking sessions at multiple facilities, and these numbers, the ROI and the estimated savings over progressive year, net present value, if you will, always turn out to be larger than expected. And that is because our machinery, our livelihood, floats on an oil film that's the thickness of a red blood cell. Anything that we can do to improve the effectiveness of that machine-saving film produces huge returns in terms of productivity and reduced cost. There's a safety improvement element as well. Overall equipment effectiveness, asset utility measure over a 5-year period. This company showed as their injury rate increased as their asset utility decreased. It's a large French chemical company, a pretty healthy study showing a tangible safety benefit, even showing correlations and risk injury to PDM type work orders versus corrective work orders. There's a lot of reasons that we should focus on doing whatever we can do to tune our lubrication program up to achieve the best possible outcome. Right product, right volume, right frequency, right product, right volume, right frequency, right location, and the right attitude. As it is today, as you look on at this presentation, your system, whatever you have in place, is perfectly designed to give you the results that you are enjoying or not enjoying today. If you want different results, you have to have a different system. So let's think about the system and how we go about achieving improvement in this system. There's 5 key steps that we would identify as systematic improvement steps. It starts with a hard, cold, objective measure of the current state of affairs such as they are today. We often find when doing these benchmarks that customers lack the detail that they believe they need and want to have for their lubrication program, improvement in lubrication program activity. So let's focus on that piece. Few challenges that need to be met when you dig into the many details associated with machine lubrication. Reliability centered lubrication is detail intensive, so you have to have a plan to organize and manage the details. Secondly, we have come accustomed to leaning heavily on our lubricant providers to tell us what the right answers ought to be. Now, lubricant providers' job is to sell products. Having come from that world many years ago, there's constant pressure to sell another product. That plan focuses on more lubricants in your plant site, where your plan should be a focus on machine reliability, starting with your most critical assets and focusing on those areas that have the most vigorous challenge to operations. What kind of details do we need to consider? Well, labor is a very important part. We need to have a thorough understanding of what our weekly labor requirement is going to be, such that we can plan our annual labor requirements. And it's not difficult to do this, but it does take having the right details in hand. You consider a critical process pump. We've got to have a plan for the motor bearing lubrication, drive side, non-drive side, a separate plan for the coupling, if there is a lubricated coupling, a separate plan for the driven machine part. Each component requires a plan, and the plan must be organized such that the work can be executed efficiently. And we do have software tools, plenty of them, that will give us the means to do that. When considering a critical pump, we need to have a plan that tells us how much labor will be required for that one pump. And then if we got 1,000 pumps, we multiply that annual plan by 1,000 to account for that particular machine type. So we have 4 visits typically to lubricate the motor over the year, 2 visits to address the coupling, 52 visits for a level check, unless we're using automation to control levels. Maybe if it's an important enough pump and we're doing sampling, maybe 4 visits to do samples and 1 visit hypothetically to do an oil change. We could conceivably measure 63 visits by a technician. We need to timestamp each one of these tasks, multiply out the timestamp per task by the number of visits to give us an annual requirement for that pump. And the same with other machine types. A direct coupled fan, for instance, running the same exercise, we may find 30 visits. Based upon the size of the bearing supporting the shaft and the speed that it's turning. This may be more, this may be less. A critical conveyor, a lot more parts to attend to and a lot more tasks or visits to each component to address the things that must be addressed to float the component's parts. So we line up all of the tasks. We see that even a relatively small production site produces a very large number of tasks. Now, we're pretty good at keeping up with the details in our maintenance departments, but at some point you have to concede the fact that a technician or two technicians working together are probably not going to be able to remember 39,422 tasks in a small production cell. The devil is in the details on our machine lubrication work plans. So to get those details in the right shape, we're going to go about devising a plan that puts our weekly work activities into routes where each task is addressed. We're going to record machine name and number, log the types, any other meaningful design details and environmental influences. We're going to, I will say you should build a map that shows where all of your assets are with respect to tanks and walls and motor control centers and what have you. This can be done easily enough in Excel. This is an Excel-generated graphic. Once you have a map that shows the view of all machines, then you can efficiently devise a pathway that gets you from one end of the production department to the other with the shortest number of steps as needed to address all machine working parts. This is the route. Once the route is defined, then we're going to go back to the machine, record details about the individual components, and there's a lot of details to be recorded. The motor, who made it, the model, possibly, the number of motors, the number of components, the fact that it's a bearing, but the type of bearing, SKF, ball bearing, deep groove ball bearing, it's noted over here, and similar level of details for every lubricated machine part. None of these detail collection bits are complex, but it is time consuming. And if we want to have a machine lubrication program that supports that red blood cell thick layer protection, and we want it to be right, then we have to have the details in order to build that plan. The environmental characteristics are also particularly important. The more aggressive the production environment, the more frequently we should be working our inspections and applications. The information we're going to use to build this plan is going to come from a variety of sources, including standardized procedures, ASTM, ISO, DIN standard procedures, and other generally recognized engineering application definitions. Let's take a quick look at what that looks like. And we'll start with bearings. And we'll start with electric motor bearings. Come on, slide. There. We'll start with electric motor bearings. We'll look at the nameplate. We'll identify the bearing descriptor number. This is an ISO or DIN standard number. We can identify that it's a ball bearing. We know that there is a limit to which grease will function well in a ball bearing. So we're going to figure out whether this particular ball bearing falls above or below this speed. It's a simple calculation. ID of the bearing plus OD of the bearing divided by 2 times the shaft speed gives us specific values. Once we know the value, we compare it for the inboard or load side and the non-load side bearing to our limit for grease effectiveness, and we get a straight up answer. Grease is going to be a good fit for this component. The next question is going to be, how thick does the oil from the grease need to be at operating temperature to give us the means to float that element? That's a simple calculation. We can either drop the details into a calculator, or we can go to our bearing manufacturer's lubrication guide and plot the same details onto a chart like this. We come up with a drop dead point. Whatever that number, whether it's plotted or calculated, multiplied by 3. In this instance, for this bearing set, we're looking at a drop dead of 15.2 centistoke viscosity at operating temperature. Multiplied by 3 gives us a target so that we're going to go try to find a grease. that gets us to 47 centistokes at operating temperature. The operating temperature is 50 degrees C. We look at a product that's got an ISO viscosity grade of 100 that we're using on motors at 50 C. That viscosity grade of 100 gives us 60 centistoke of working viscosity. We said we wanted to have 47. That would be ideal. As it turns out, the product we're using would be ideal, and we move on to the next step. When calculating the viscosity requirement, we want to get to a space between 3 and 5 times that drop dead value. That is obviously greatly influenced by the operating temperature of the bearing. So we also need to know the operating temperature of our bearings and other lubricated machine parts when we're designing a program. Step 6 is about lubricant selection. Bearing manufacturers along the way have said it would be better if you're not using EP formulated products. EP attributes by design are somewhat corrosive, can particularly attack soft metal surfaces. If we don't need EP formulated greases, and we shouldn't use them. The drop dead viscosity value is the break point that tells us whether or not we should use EP products or not. In this instance, we picked a product that puts us out here just above 3 times the drop dead point. So we don't need EP formulated products to be able to expect to protect the bearing surfaces. The 6th point would be one of volume. It's a simple calculation. We want to fill the space that exists between the axial planes and the vacant space around the element. We calculate that 0.005 times the outer diameter of the bearing times the width of the bearing gives us a value in grams. That's a simple formula, works on all types of bearings. This is the correct volume defined, and then we can verify that with different tools. We can put in the precise amount if we have the right equipment. Using ultrasonic energy testing, we can even demonstrate that we need more or less dynamically. The last point is about the frequency. Now, if we need more grease in a bearing, we should adjust the frequency to get there. Within a few seconds of supplying the grease to the component, all of the fresh grease will have flushed out the raised faces, and now it's sitting on the sideline. If we need more grease over the course of the working duration, then we need to take our big interval and chop it up into smaller pieces. All of our bearings would really rather be lubricated with oil, but we can approach that kind of attribute using grease if we are planning and scheduling the right frequencies. Here's a formula that can be used to determine a frequency. It is modified by the K value, which is the environmental conditions around the operation, the speed, the bearing temperature, the contaminant load, the moisture load, presence of shock loading, whether it's a horizontal or vertical axis shaft, and then the bearing type itself, all factor in to determining how frequently we ought to be lubricating the machine parts. None of these details are complex, but they all need to be captured and factored in if we want to have a precise lubrication work plan. Along the way, including from the previous discussion, we heard consideration about condition monitoring as a means, lubricant condition monitoring versus vibration-based bearing condition monitoring. Well, an option for our grease lubricated components is ultrasound measurement. Ultrasound measures contact energy. It's a much higher frequency than vibration energy, which measures the movement, not the contact. Ultrasound tells us when the asperities are beginning to bump and collide, and if we have high decibel values, that means our bearing surfaces are approaching a dry state. When we lubricate, we refloat the surfaces, the decibel value declines, consistent with less contact energy, and we're able to use this to dramatically, I shouldn't say dramatically, to effectively control volume being supplied for each component. There's rules for bearings. There's rules for couplings. Different kinds of couplings, different centrifugal force values related to the operation of the coupling. Different greases would be applied based upon the degree of centrifugal force loading on the grease. It's all fairly well objectively definable. Grease characteristics for those 3 different types of greases. We need to pick the right type of grease to match up with the coupling's operating conditions. There's rules for gear drives. So whether it's bearings, couplings, or gear drives, all rules ultimately boil down to speed and size of the machine part. The pitch line velocity is the required working viscosity for a given gear wheel in a gearbox. We know the pitch line velocity, which is a calculated value, pitch diameter in millimeters times the speed of that wheel divided by. And if we know the temperature of the oil in the machine, then we can clearly identify the best fit lubricant that fits that speed at that temperature. Very objectively definable. Fortunately, our gearbox manufacturers have done a good job of defining this and putting information on nameplates that go on our gear drives. They've done that for us. The pitch line velocity is the speed that this dotted line is moving in circles. The pitch diameter between the 2 gears is the point where load is transferred and rolling contact occurs. So that's the critical value. The gearbox manufacturers many years ago began putting the correct product definition according to an operating temperature range on their machines. All we got to do is go look at the machine, get the correct temperature and or the ambient temperature, and match up what the provider is providing, the lubricant supplier is providing, or the technical spec for the machine itself. Gearbox manufacturers use nomenclature for lubricant definition that's similar to what the rest of industry uses, slightly different, but the match is easily made. So regardless of the component, we got some calculations that we need to do to come up with the objectively defined best possible plan for all of our machine parts. Now we might well conclude, yeah, we don't have enough money in our budget to do that for all machines. Well, that's fine. Focus on the top 20% critical assets. Those are your bread and butter and safety concerned assets. Focus on those. Build the plan. Live it for a year, 2 years, 3 years. Begin to enjoy the benefit of that plan and see how it works out, and then transfer that well-defined, precise lubrication plan to other assets. There are tools that assist with the aggregation of the details. This tool called Lube Coach Pro is useful for getting all of the machine details together in one spot that gives you, the user, the means to produce an output that represents a vigorously defined lubrication plan. From there, it is tempting to try to put all of this information into conventional CMMS programs. We have many: J.D. Edwards, Maximo, SAP, well-known, excellent programs, excellent software, but those programs do not provide spaces for these details. So as it turns out with conventional CMMS, you're writing up individual work plans based upon text scripts. Go find yourself a task management system that gives you the means to organize your tasks in that linear sequence that you've defined. And then when you schedule that particular production department, you have the tasks that are due for the week that are all assignable and trackable to. And if you pick a system that gives you this feature, you might even be able to recycle tasks that were simply identified as incomplete without any extra effort. Here's an example of a written output. Mostly people today are using tablets to keep up with and record the completion of these details, and that's the smart approach. Your task management software should also, because all the details are based upon data fields, should also give you the means to generate rich reports on important things like what percentage of the task did we get done this week? How were we doing for this month in completing tasks on the first schedule? Now we should be at 90% task. And if we can't get there for a given route, then we need to move tasks around to other people, redistribute the workload so we can consistently hit 90% of task completion. You might want to track lubricant consumption. How do we control cost if we don't know where the cost is incurred? Anything that is a within your system can be turned into a query and output. And with the benefit of our business intelligence systems today, that information can roll right out the front gate electronically up to the corporate office. And now we're not fielding phone calls every time we turn around either. Without a quality plan to manage the many, many details and a real, true getting those details accomplished each week, we are likely to drown in the complexity of our machine's set of lubricated machine parts. We need a plan. A good plan will provide us the means to govern our work practices and control mechanical reliability of all lubricated machine parts. There's always room for improvement as well. Targets, 90% completion. Review oil analysis results bi-weekly. Implement vigorous contamination control limits. We didn't get into that, but a huge influence on your success, particularly for oil lubricated machine parts, is contamination control. Your technicians need to contribute from the chin up, not just the chin down. They need to have an education in the basics of machine lubrication, understand what the relationships are, understand the why behind the what you're asking them to do. And then you should look at your program on a quarterly basis to compare against your existing reliability goals and see if you're still moving in the right direction.
So I'm just going to have to jump in a little bit because we're just almost at the closing time. And I know we had just one question.
Yep, go.
So we had one person, Mohammed, asking if there was a relationship between the motor grease drain point and the exploration area. So I'm just going to bring that up on the screen here for you to help us a bit. So is there a relationship between motor grease drain point and the exploration area? Because we were talking about the exploration area in terms of, determining where we could get that perfect grease point and that, trying to figure that part out. So can you help us with that?
All right. There's a misnomer about drain. The grease that goes into the motor is going to stay in the motor 9 times out of 10, regardless of how much grease you attempt to push into the motor for flushing purposes. You're not going to get any grease out. So that excess grease is going into the stator cavity and will corrupt your motor. I'm not sure what exploration area. I'm not sure what we're leaning on there. Sonia, if you could provide him with my email address, we can beat on this more thoroughly.
Definitely, because that was one of the main questions that we had there. And I know that, like, just from the information that you shared, very detailed, very interesting things. We always need to be able to, calculate the right grease that we're using, because half of the times we're not using the right grease or the right viscosity. Yeah, suited for our temperature, suited for our operations. So I'm so glad that you were able to share that with us today, Mike.
Yes,
and
ma'am.
I appreciate so much
Thank you for
taking
the
time
chance to visit with you.
to stay with us and share that information. I know some people were asking about the slides and if they can get access to the slides. I'm going to leave that up to you, Mike. If you all want, reach out to Mike Johnson. He is on LinkedIn. And of course, we can provide his email address to you once you just send us a quick note.
Sonia, if you like, I can send a PDF copy to you for distribution, but I would love to hear from your attendees as well.
Oh yeah, because we always like to hear feedback with LRVS. It's a community after all. Yes. So that's what it's about. But thank you so much, Mike, for your time. That was one of the main questions that we had. I know we'll have some others coming in. And I love the fact that you set the stage for Blair and talked about ultrasound. Well done. Because he is up next in the next 5 to 7 minutes. So we will be seeing him soon. So all of our attendees, you have a little 7-minute break in between. And we will be back in a little bit. Yeah? All right. Thanks, Mike.
Thank you.
Bye.